This is the Core Course A. Welcome. It's very nice to see your faces. I hope you're not too hungover or tired or whatever. I am Alan. This is Michael. And there's Stephen in the back there. And we're going to talk to you about how IPFS deals with files. Part 1 of 5. It's all right. They're exciting, I think. Well, that's been the feedback so far. All right, first up. Okay. Can anyone tell me what the meaning of the word immutable is?
Can't change.
Yeah. All right, awesome. Unable to be changed as opposed to mutable, which is liable to be changed. So we're going to talk about why IPFS has a big focus on immutability and immutable data. In a peer-to-peer network, the one on the right, there's no central point of authority, no one to implicitly trust. But in the web of today, we implicitly trust kind of things like institutions, so certificate authorities, social media, government. But that trust is easily subverted, and we can't necessarily rely on the data we receive to be the data we ask for, even though we often do. Resource integrity checking is one way to ensure that data you ask for is the data you've got. The idea is to calculate an identifier for the data from the data itself. The identifier is called a hash, and we use cryptography when computing the hash to ensure certain properties like uniqueness and determinism, but we're going to talk a little bit more about that in the next section. So once we've got this hash, we can share it with the rest of the world. These two people being the rest of the world. And when someone gets hold of that data, they also calculate the hash. And then they check that they match. And if they do, then yes, you've got what the data you asked for, winning. If someone else gets hold of the data and the hashes don't match, then someone's tampered with your data. So the guarantee of integrity checking is that content is immutable. If the data changes, the hash I generate no longer matches. So verifiability is one of the main reasons for using immutable data. In the web of today, I can put my poodle picture up at abc.com/poodle.jpg, and 24 hours later, I can doodle on my poodle. So let's say I add some glasses, make him look a little bit more sophisticated. So the problem is that the content isn't inherently tied to the address. The content can change, but the URL doesn't. So depending on when I access this poodle, it could be completely different. So what we have on the web today is location addressing. It tells us where the data is stored, but not much else. Content addressing, on the other hand, is where we use a hash to access the content, and it allows us to verify the content we receive is the content that we asked for. Okay, caching and deduping. Immutable content completely solves the caching problem. Since the data is never going to change, the cache rules are cache this forever. So back to our example, if we were using content addressing, our cute poodle has a specific address derived from its content, the hash. And if I change that poodle 24 hours later, the address also changes. But that's okay. It can be verified, cached, and fetched by anyone. What if I wanted to keep both files? Well, because the content is immutable, IPFS only really needs to store the changes, the differences. The two files that we see actually share many of the same bytes. So if I have one of those files, the amount of data I have to transfer to fetch the other is really minimal. Currently, if I want to store those two very similar pictures, I need to store both of them in full on my disk. And if I want to share them with someone and I want them to see both of those pictures, then I have to transfer them both in full. And we'll see more about how IPFS does that magic deduping stuff later. Okay, fetch from anyone. If the content is immutable and I can verify its integrity, I should just be able to get it from anyone. And this suits P2P really, really well. But that's not true of the web today. So I have two sites on the net hosting the same content. How do I know which of these poodles is the correct poodle? Well, okay, so the answer is that we can't trust that any of these poodles are correct. They are both adorable poodles, but we just can't get it from anyone. It needs to come from a trusted source because I can't verify its integrity. All right. So we use content addressing in IPFS, and we use a special hash called a CID. CID stands for Content Identifier, and we're going to take a closer look now in part 2 of 5. Okay, it all starts with cryptographic hash. A cryptographic hash function maps input of arbitrary size to output of a fixed size. And we want a few properties from that hash. The same data should always produce the same hash, so it's deterministic. It should be impossible to invert, as in we shouldn't be able to reconstruct the data from the hash. It should also be unique, so no two different files should produce the same hash. There are many different hashing algorithms that exist. IPFS uses SHA-2256 by default. That is just some of them that are available in IPFS that we could use. Older algorithms like SHA-1 are broken. They're proven to not be collision-free, and the problem is that if algorithms can break, we're going to want to switch that hash that we use by default in the future. The problem with switching algorithms is that given a hash, which is just a series of bits, what algorithm did we use to generate that hash? We need a future-proof way of identifying the hash function used to generate a hash, as well as the hash length. Say hello to multi-hash. It'll solve all your problems. So a multi-hash is the hash, which is just at the end there, but it's also a prefix. And that prefix is one number, algorithm, and which identifies the hash algorithm that was used to generate the hash, and another number, which is the hash length. These two numbers are both variants, and variant is just a compact encoding for integers. The algo number is a multi-codec because A, it's a variant, but B, its value is a predefined value that we agree on. It's in a table on the internet. The multi-codec identifier for SHA-2256 is the number 18, and our hash length is 256. In binary, it looks like this. You'll see that the hash length is actually 2 bytes long, and that's because the length is over 127, and in variant encoding, numbers above 127 are encoded as 2 bytes. So you can kind of think of this as like 2 times 128 is 256, but that's not really how variant works. That's just a coincidence. But yeah, 2 bytes because it's over 127. We want to support multiple encoding of data. So you've got a hash that addresses your data. When you get the data back, how do you know how it's encoded? Like it might be encoded in CBOR, concise binary object representation. It might be encoded in protocol buffers. It might be encoded as just plain old JSON. Why do we want this? Well, it might be a particularly compact binary encoding, so really efficient for storage, but it might be for convenience, might be just easy, it might be really quick. But we have this same problem again. Like when we're looking at some encoded data, how do we know how to decode it? Same solution, more metadata prefix. So this is an IPLD codec, and IPFS at the moment, any content that you add gets the codec we use to encode the data is DAG PB, and it is PB stands for protocol buffers, so it's just protocol buffers encoded. Yeah, and it's like I said, it's a compact encoding for the data, and we add some metadata to the start of the hash.
Are there other codecs currently?
Yeah, there are many IPLD formats that you can use. There are too many IPLD formats. All right, so there are 2 different CID versions, so that's mildly frustrating. But so often nowadays, or hopefully going into the future, you will see version 1 as the main version that we're using. There's version 0 and version 1. It's just another prefix that we add on to the front. So all of you, if you've ever used IPFS before, you might be used to seeing CIDs like this. Version 0 is the top one, and the version 1 is the bottom one. So the version 0 ones begin with kind of QM usually. Version 0 begins with QM. Version 1 begins with BAFE or BAFK sometimes. All right. So the thing is, CIDs are binary datas. Zeros and ones make for really long strings when they're printed out. Like, it doesn't even fit on the slide. So what we do is we use a higher number base encoding to make them shorter and easier to print out and recognize even when in string form. We have another problem again. How do we interpret the number base encoding that this string was created with? Characters in one encoding are valid in another encoding, so we can't just look at the string and be like, that's a base 32 or that's a base 16 or whatever. So how do we fix that? Well, you guessed it, more meta prefix. This is multi-base, and multi-base helps us know the number base the content is encoded with. The first symbol is the identifier for the encoding. B is base 32. Z or Z is base 58 BTC, and M is base 64. Version 0 CIDs, like the QM one you saw in the last slide, are also base 58 encoded, and I just told you that base 58 should be prefixed with Z, but they're not. If you're wondering about that, then don't worry, we will talk about it in a minute. Okay, so the rest of the string after the first symbol is the rest of the CID encoded in that particular base. So altogether, for a CID, this is what it looks like. In binary form, it's the CID version, it's the IPLD format multi-codec, and it's the multi-hash. And the multi-hash is split up in, as you know, because we just covered it, into the hashing function used, the hash length, and the hash. As a string, we have the multi-base encoding, and that encoding applied to the rest of the CID. Cool. All right, so you can try this as well. If you fire up your browser and go to cid.ipfs.io, and if you have a CID happen to have one lying around, then you can paste it in to that tool, and it will pick out these properties that we've just been talking about of the CID and show you them. There's a tool in IPFS, if you've got it installed on the command line, called IPFS CID, and that will allow you to change the number base or the version number of a CID. If you type IPFS CID --help, it will tell you how to use it. So if you've got like a V0 CID and want to convert it to V1 and put that in or whatever. But anyway, I'm gonna open this up now and show you a few pre-prepared some CIDs I prepared earlier. If I can figure out how to open it up, it won't connect. Of course, I need to have my daemon running. All right, so this first CID I have, back to the start of the string. This is a BAFE CID. This is a base 32 encoded CID. Oh, hang on, let me make this a little bit bigger for you. Version 1 CID, it's encoded with the IPLD format called DAG-PB. We've got the multi-hash at the end, which is the name of the multi-hash. Name of the hashing algorithm is SHA-2 256. The length is 256, and that is the actual hash. So multi-base, as I was saying, is its code is B. Start of the string is B, so that's good. That matches up. Base 32, DAG-PB. For the multi-hash, the code for SHA-2 256 is 18, as you saw on the slides. So yeah, that's one. I've got a base 64 encoded CID here. If I paste that in, if you remember I said that base 64 CIDs start with M, and they do. according to this. It's all good. So this is another CID v1, and yeah, base 64. I've also got one here with a different IPLD format. Oh, whoops, sorry. So this is a v1 CID encoded with base 58 BTC, and this is interesting because it's using a DAG CBOR IPLD format, not the DAG PB, which is the DAG PB is the default for adding files in IPFS, but you can use the IPFS DAG API to create structures that have different encodings, and this one's good for like JSON data. There we go. Okay, and so finally, the one you've probably all been waiting for. What is going on here? All right, QM. This is a v0 CID, as you can see here. QM. Begins with QM. It's encoded as base 58. But what have we got here? Multi-base code implicit? Multi-codec code implicit? What? Should we talk about that? Yeah, yeah, right. Cool. That's good, because I've got slides prepared for it. All right. In the beginning, there was only multi-hash, and they were encoded as base 58 BTC. All version 0 CIDs have no multi-base. And so that's why they don't start with Z. Why do they start with QM, though? Well, they are just multi-hashes. And they're just multi-hashes encoded with base 58. So if you remember back to the slides about multi-hashes are the hashing function plus the hash length plus the hash. And those two things at the start of the multi-hash are kind of fixed usually in IPFS, so which is why you see a lot of these. And it's just what it is. This QM is just those two numbers encoded in base 58. The multi-base is always base 58 BTC, like I said. And so what else do these not have? If version 0 CIDs are just multi-hashes, what do they not have other than not having a multi-base? Anyone?
LD format.
Right. They don't have a format. They don't have a CID version. So altogether for V0s, this is way simpler. They're just multi-hashes. And in string form, they're base 58 encoded multi-hashes, which is why they start with QM. You can kind of think of them like this. So the multi-base is always base 58 BTC is Z. It's implicit, it's not written. CID version is always 0. It's implicit, it's not written. The IPLD format is always DAG-PB. It's implicit, it's not written. The hash function is always SHA-2256. It's explicit, not implicit. It was a trick question. It's in the multi-hash. So the hash function is in the multi-hash. It is there. The hash length is also explicit. It's in the multi-hash. And if any of those variables change, then you don't have a V0 CID anymore. All right, cool. So now you know how IPFS addresses content using CIDs and hashes, and we can now learn about the data structures that IPFS actually addresses. So cool. I'll hand over to Michael.
Yo. Hey, everybody. All right. Now that we've done this 3 other times, this should go really, really well. So, what's a DAG? I'm sure that you've probably heard at this point people throw this term around a little bit. DAG is just a fancy acronym for directed acrylic graph, which is a very fancy word for a really simple concept. If you think about a normal tree structure, you have a root and then some branches and then eventually some leaves. And typically in a tree structure, a leaf would have one parent. In a DAG, it's a tree, but a leaf could have multiple parents. You can't have circular references. We'll get into that in a minute. And that's impossible, but that's all that it means. It's unnecessary gobbledygook. So let's build a DAG. So one interesting thing about building hash-based data structures is that you have to build them backwards. So get used to writing recursive functions. I hope you enjoy that. So we're going to start here with hello world, just our little object, which is the leaf node. We're going to get a hash of that. The hash is qm hash 1. Now we build the first branch to that leaf node. That's going to be an object with a property of foo that points at this leaf node. That's going to get qm hash 2. And then we can create another leaf node, all pointing back into a parent. So this one has a bar property that points to the same leaf node, and another property that's just some arbitrary metadata. And both of those are referred to in the root, so they both get hashed and then used as properties in the root node. So what you end up with is a full data structure that looks something like this, right? Now, in this one, you can't tell that these are basically pointing to the same thing, but semantically, this is a big data structure that you get. And then you can break that into blocks like this. Now, obviously, this is a very tiny data structure, so we wouldn't normally break this into a bunch of blocks, but when you have really arbitrarily large data structures and you want to break them into smaller semantic blocks, this is how you do it. You do it with linking. And the way that links end up working in any API, in IPLD, or in IPFS, is that they get traversed basically transparently. So if you take the hash of qm4, which is our root node here, and you follow it through 1 through hello, you traverse through the entire structure until you hit this hello thing, right? And it's just going to grab all of those blocks for you and traverse it transparently. But you could also grab the hash of one of the leaf nodes here, like qm hash 3, and look at a property there. You could grab the hash of the leaf node itself and look at a property, right? So if you already have the hash of any of these branches, you can traverse it even more efficiently. Here we go. So if we look at the tree now, sort of in a top-down way, where the links are sort of pointing down, we can talk about some of the nice constraints of making DAGs. So we see here that we have 2 branches pointing to the same leaf, but what happens if we try to create a reference back to the parent? If we basically try to create a circular reference. Well, it's actually impossible, because if you modify this, you're going to modify the hash. And because the hash of this is part of what is inside of these leaves that are included in the roots hash, then that would change the hash of everything all the way up. So this knowledge, what the hash would be of the root node, is just impossible to know up front, unless you have a hash function that's been broken. So if you don't use SHA-1, bad things can happen. So any questions before we get into sort of block sizes and a discussion about that a little bit? No questions? Cool. Okay, block sizes. So block sizes are like the 3 bears. Too hot, too cold, just right. So blocks can be too big, and there's when you start to make blocks bigger and bigger, you get a set of different problems. One big one is that you can't download a single block from multiple peers. The problem is that in an untrusted network, anybody could just give you bad data. The only way that you have to validate if the data was right or not is the hash of the entire block. So if you pull data from 2 people for the same block, and then it doesn't validate, who sent you bad data? You have no idea. So BitTorrent has been dealing with this for longer than anybody, and they just don't try to do that anymore. If a peer is too slow and they decide to take it from a new peer, they'll just download all the same data again. So when you have these large immutable structures and then you mutate them, you get a new root, which we'll get into in a little bit. You end up creating what are called orphan blocks. If you've ever built databases or dealt with any on-disk mutable data structures, you deal with the same problem, where as you change things, you end up with data that's just garbage that then has to get collected at some point in time. So when you have really big blocks, that leaves you with really big orphan blocks, and then those really big orphan blocks create a bigger GC problem. Different transports may have different limitations. BitSwap has issues with blocks over 2 megabytes right now. That will probably be fixed, but you should still try to keep that in mind, and keep in mind that other transports are going to have similar issues. You also end up with a lot less deduplication the bigger that you make the blocks. That's because the only method that we have for deduplication is the hash itself. So if you take all of these little particles that would be the same data across many different nodes, but they're not links, they're just embedded in the blocks, then those won't ever get deduplicated. Too small. So you also end up with issues when you make a bunch of tiny blocks. So the big one is that you just end up with more requests for more blocks. If you want to get like a small amount of data, you end up getting like a lot of different blocks. That could be out of the network, that could be off of disk, but it's always going to incur some kind of round trip, usually to I/O, unless you have like a lot of in-memory cache data. You also end up with more encoding time. When you write different block encoders, you can make them more efficient the more data that you have to encode at a time usually. So if you have a much smaller sets of data, then you may end up with less efficient encoding times. The big one though is hashing. Hashing functions usually have guarantees about how long they're going to take for any amount of data. So if you end up with a lot of smaller blocks, you're going to end up with like many more hashes, which is actually going to spend like a lot more compute time on all that hashing. And then, so similar to the block request, you end up with just more hops to a given piece of data. So whenever you want to look at something through a deep graph, you end up like going from one thing to the next. And the more that you create, the more links in that chain that you create, the more potential performance impact you have. So what's just right? Just right like very much depends on your use case. There just isn't one true way to do this, unfortunately. This is why we've created so many flexible structures in how you create blocks and how you create your DAGs, is that different use cases are going to call for very different DAG structures. So if you want to optimize for reads versus writes, if you can take a lot of performance cost up front at write time to make the reads really fast, you might do that. If you have often when you have mutable structures, you will not actually mutate a particular part of the graph, but you might just recreate it every time. A good example of this is like when IPFS creates a file and chunks it up. We always pull that whole file out of disk and then run it through the chunker. We don't like look at the existing chunked file and go like, oh, I see like a particle that I can just stick in here, right? Like, in order to figure out if they match, we just re-encode it every time. And so you would use a very different algorithm to create that DAG and balance it essentially. Than you would if you were just trying to mutate a DAG over time, right? HAMP is like a really good example of like something that you mutate in place really often, and so there's an algorithm in a HAMP that guarantees a certain balance and a fixed width, or sorry, a fixed depth of how big that tree will get. So these are just like different trade-offs that you can make when you're deciding how to create the DAG and how much and how big you want to create the blocks. You also have transport performance issues, right? If you're pulling all of your blocks, out of like an HTTP2 connection to one host, it's going to have a very different performance profile than pulling them out of peer-to-peer network. And so you might be able to make completely different trade-offs when you're creating those block structures than you would otherwise. So that's. Oh wait, any questions before we break? Actually.
Can you go back one slide?
Yeah. Cool. In the back.
So I think you're alluding to this, but basically right now for arbitrary data, there's no optimization to try and figure out if there's overlap. Like if you're just mutating a little bit of a file, that most of the blocks will be the same out of what you chunked, right? But if you change something that's arbitrary, how do you figure out what that arbitrary bit is? Can we leave the rest,
Yeah, so it turns out that particular problem in the file case is dependent on the file type. And there are different chunkers that you use to potentially get better deduplication out of different file types. And so we will actually get into that a little bit later. I think we talked about Raven a bit, right? Yeah. So like if you have text, Raven is like an algorithm that breaks it up in a really nice way to do the deduplication.
Next section.
Yeah, that'll be in the
That's
next
your
section.
section.
We promise. Yeah. Any other questions about DAGs and block sizes? Yes?
Do you believe that the current algorithm is very efficient, or is there still a lot of work that's going on?
Which algorithm?
The production of the DAG for anything that's put into add, for example.
I think that we have some good options. So the problem right now is that we are not pre-configured for different data types to use different chunkers. You have to tell it which chunker. I think that we have some really good options in which chunkers to use and pretty decent defaults in the chunker. I think that the thing that we're not very efficient at right now in UXSD 1 is the DAG that leads up to the file. So the directory in the files, right? So like if you have a really tiny file, we don't have a way to like just inline that binary into the file, and then if that file is really tiny, inline it into a directory, right? Like if you had a directory of 5 files and the entire set was like maybe like 1/10 of a megabyte, just one block, like who cares? But we don't actually have a way to do that in DAG-PB right now. So in the Unix SV2 deep dive later today, I'll get into sort of how we might solve some of these problems. So I think that we don't have a very efficient way to create the DAG leading into a file, but once we get into file chunking, we've done some pretty good work there. For sure.
Are there some plans? Sorry. Are there some plans to have an inference sort of for associating file type or depending
Yes.
on file data?
Yes. Yes. But in Unix SV2. Yes. Uh-huh.
So a block is like a blob of data, which could be more than one or more files, or is it going to just have it be one file? Like if I have a text file, that's
Mhm. So
if
right.
I have like 10 files in my repo.
Mhm.
how does
That's
it-
many blocks right now. So right now in UCC1, that's going to be one block for the for sort of file metadata, and then at least one block for the actual file data that is linking to, and then the directory around it would be another block that links to
So
those.
a block wouldn't contain more than one file.
So they will in the future. I think that like if you're just thinking about DAG sort of generically, the way that we've done things sort of throughout the stack is that a block can contain an arbitrary number of what we call nodes, right? So a node is like any map or any value within it. We don't have in newer codecs like DAG-CBOR and DAG-JSON, we don't have any sort of limitations on how deeply you can go in that and what types that you can use. So in the future, I would say like yes, one block could contain many files, but right now there are some bigger restrictions on that. There is. To answer your question, you should not think of a one-to-one mapping between a file and a block, or really any data structure and a block. Yep.
Did you have a question?
Okay, actually, a question.
Okay.
Unix FSB2
Mhm.
it's not added, right?
No.
All right. And then?
There's
is
a
that?
there's a deep dive. Yeah. It's like
It's-
being developed.
It's your break time now. So
It's your break time, yeah.
You should.
We're bleeding into
Next
the break.
section is like how we get a file into IPFS and what happens to that file and what DAG structure it creates.
Yeah.
And we'll do some examples. So if you have like, if there's more questions around that, then I
Yeah.
encourage you to save them until after that section.
Yeah.
And
Good
go
idea.
for your break now because we've got. So if you come back, we'll just do 5 minutes now. If you come back at 1:45, then we'll start again. Okay. Okay, let's get into some deep diving into how importing files works in IPFS. There are fewer people here, but I'm sure they'll shuffle in. All right, let's get started. What actually happens when I use IPFS add? My file here is a tube of bits, and what actually happens is that those bits get divided up into chunks. Chunk 1, chunk 2, and chunk 3. I'll be referring to them later, so just if you see C1, C2, C3, these are the bits of the file, the chunks of the file that get chunked up. So these chunks are arranged into a tree structure, which is a DAG, and so we already talked about like items in the graph are called nodes. Not every node needs to contain a chunk of the file. Some of these nodes are intermediate nodes. They could contain chunks of files. They don't always. In this example, they don't. So yeah, we've got the chunks in these 3 chunks in the leaves of this DAG that has been created. When building the graph, we already talked a little bit about this, but we calculate a CID for every node, and that happens from the bottom up. And that happens because we can't calculate the CID for the parent until we know the CIDs for the children, because the CID is calculated from the data as well as any links it has. So if the links, we don't have the CIDs for the links, we can't calculate the CID for the node. And so we have to start at the bottom here and come back up, and at the top we can't do the top one because we don't have the one below it, so we have to traverse all the way down to the leaf and then slowly make our way back up again, and we finally get to the root CID QM#6, and so for a single file this is the CID that is returned to you, and you can think of this CID as the CID for your file, but actually it's the CID of a node at the top of a tree, which makes up your file. Okay, so let's see it in action. You can try this out in your browsers as well. dag.ipfs.io. Drop a small file, like less than 100K, onto it. People have been dropping like 5 meg files on it, and I've set the chunk size pretty low, and like their browsers start like whirring, and because it's trying to render a graph. So what it does is it renders the DAG for you, and it's trying to render a graph of like 1 million nodes. So yeah, just drop a small file on it. So here we go. If you go too small, then you'll just get a single node. So like, there's a sweet spot. All right. So here we go. You should see something that looks like this. Let's just move these up a little bit. Oh, hang on. Let's close that. Don't need that anymore. Oh, yeah. Help if I had my folder of bits on the desktop, wouldn't it? Right. Okay, so you should see something a little bit like this. Where's my notes? Okay, so what is this? This is a tool that runs JS IPFS in your browser. If you drop a file onto it, it will draw the DAG that gets created. So what we can do is we can drop a file on. Oh. Right, we can drop a file on. This is the README from the Go IPFS repo. And it will render my DAG for me. And then I can hover over nodes, and I can see that on the bottom here, we've got a bar which tells us information about each node that's been created in the DAG. And we can see that each node has a different CID, and they're put here. They're displayed here. And then I can change things like the chunk size. At the moment we're creating 5 12-byte chunks, but I can change that to 1024, and I get a graph with far fewer nodes because each chunk is able to have much more data in it. I can push that up to get an even smaller graph and go all the way. This is the default chunk size in IPFS. I just get a single node for this small file. There we go. Cool. So back to the slides. All right, we've already talked a little bit about this, but why vary the chunk size? So the default in IPFS at the moment is whenever you add a file, just to chunk it up in fixed chunk sizes. We have a default for that, and we've just been changing that a little bit. But like smaller chunks, potentially because they've got fewer bytes in them, we've got a better chance of deduping them. But it, like Michael's already said, it's more work up front to create all of those chunks. You have to create hash the data, and for the CID for every single chunk. And the more chunks you have, that's more work up front. If we have larger chunk files, then that's less work up front, but easier to, like, there's fewer nodes to traverse when you're transferring the data, fewer nodes to transfer, but it's not so necessarily so great at deduping. Smart chunk sizes, on the other hand. Now that's an interesting one. So like maybe you have a chunker that chunks at keyframes so you can have better seeking in videos. How cool would that be? Or it might be a chunker that does like very cleverly chunks the file so that if you add data in the middle, it doesn't throw off all of your. So the problem with like fixed chunk sizes is that if you add a bit of data in the middle, then everything, like, it throws off the rest of the chunks, and those chunks are now different. And so the deduping is not necessarily as good. If you use a smart chunker, which will take that into account, maybe give you a chunk that's a little bit bigger for that data, then you can keep the same chunks that you had before for the rest of the file. So we have a smart chunker already. It's called Robin. You can use it in JS in the browser. Which is brand new, by the way. It's like a little WASM thing, which is super cool. And it's in that DAG visualizer as well, so you can check that out. Smart chunk size is really interesting, but again, it's more work up front to do that work of kind of figuring out where is the appropriate chunk boundaries.
So that's always content specific. You have to know what type the data is.
Well, so Robin doesn't know.
Oh, okay.
Robin just takes a stream of bytes and figures it out. It's very clever.
Okay.
It is crazy old rsync magic.
Mm.
Okay.
It's been around for a long time. It's not IPFS specific. But yeah, so at the moment we have these two chunkers like fixed and Robin, but like we could have many different chunkers for many different file types that would do the right thing based on the file, and you know, we could have some really good deduping, good chunking. Anyway, okay, so back to the example. Let's look at deduping in the visualizer. All right, what I've got here is I've copied the README, and what I've done is I've just added some data to the end of it, so it's a little tiny bit bigger. And what I can do is I can drag and drop that on here, and what the visualizer tool does is it adds a directory for these two files. So these two nodes directly descending from the directory are the two files that I've added, or the roots of the two files I've added, basically. And you can see from the lines in this graph, they actually share almost all of the nodes, apart from, so right at the end here, so we can pick these up and drag them, we can see that there's two little chunks here and here, which are the only two chunks that are not shared by these files, which is kind of cool. And you can see that this chunk, if you look at the byte size here, this chunk has slightly more bytes than this one, and what's happened here is that I haven't managed to get it so that it's on a complete boundary. So there will be some shared data in these two chunks, but one of them has that extra bit of data that I've added to the file. So yeah, this is deduping, and this is how the two very similar files on disk can don't actually take up 2 times storage space in IPFS. Right. Okay, so actually, I've not told you the whole truth about this. The nodes in the graph are not just made up of the chunk of the file data. Every chunk is wrapped in this thing that we call the UnixFS wrapper. And UnixFS wrappers they can either be files, they can be directories. There are other types, but these two are the main two, and it allows us to distinguish between what is file data and what is a directory. So it's kind of a dream within a dream. It's not just the data; it's a wrapper, and that becomes the data. So what that does is it actually adds like a few bytes of overhead to every node, because we've got the UnixFS wrapper around each bit of data. So let's take a quick look at that in here. Okay, so we can see in the bottom left-hand corner, if you hover over a node, the UnixFS type that node has, and this one at the top, as I said, what the tool does is it puts 2 files in a directory. So this is a UnixFS directory, and these other nodes are all kind of UnixFS file nodes. And so we can see the total bytes that make up this node and the bytes of data in this node are slightly different. And that's because there is this UnixFS wrapper. There's a few bytes of wrapping data that is in every single node. What we can do is we can change the leaves to using raw leaves. And what that does is instead of adding the UnixFS wrapper to the leaves, it will not do that, and it will just add a raw buffer of data as the leaf. And you can see that the bytes total for these nodes are exactly the same as the bytes of the data. So we don't have this wrapper anymore, and that means that we save a little bit of space on every node we create because we're not wrapping it with any information. It also means that we get a V1 CID. So you can see here, this is a V1 CID. So these ones are start with QM. That's a V0. These ones start with BAF K in this case.
Why is the CID different? If using,
So the CID is different because
I know where the hash is different, but why is it a different format?
CID v0s, as we talked about earlier, they have implicit things about them. One of those things that is implicit, that is not written, that means it's a v0 CID, is the IPLD format. And the IPLD format for these nodes is DAGPB. For the raw nodes, so the IPLD format, if you remember, tells us how to decode the data. So we know that what this data is, it's a protobuf encoded chunk of data, and I decode it with using as if it were a protobuf.
Yeah, okay.
So this is just raw bytes, and so this has the IPLD format, IPLD raw.
But why wouldn't you just use V1 for the Unix FS as well?
For these ones, that's a good question. And I think the answer is it will be soon. We're kind of in the middle of transitioning. At the moment, if you IPFS add things and specifies this CID version to 1, then you'll get a V1 CID. It's just because this is what people are expecting at the moment, and it's a big breaking change to switch to V1s because suddenly the CIDs you get back are completely different to what you would have got back before. So like I said, this is now a V1 CID because it's using a different format, and it cannot be a V0 CID because it's not a DAGPB encoded data. Cool. So that's that. All right. There's also different graph layouts that have different performance characteristics. Balanced layout is the default you get when you IPFS add. It's really simple to build. And really easy to traverse, but it's kind of difficult to edit. If you were to change in the middle, you'd have to do a lot of rebalancing to kind of balance it out again. Whereas like we've got trickle as well is an option. It's more difficult to build, but it's really great for like streaming, for example, because the time to first byte is a lot less. Like you can imagine, like if I have my data in this leaf, then to start streaming, I need to get hold of this node, and then I need to get hold of this node, and I can start streaming. Whereas like, imagine I've got a big file, like a big movie file, and it's made a big balanced DAG. And if I want to start streaming it, then I'm going to have to get this node, potentially this node, this node, and this node, before I can start streaming. So the time to first byte is going to be much better with a kind of trickle style DAG. Cool. All right, so let's take a look at the two different types of DAG layout that we have available. All right, so this is the balanced layout. This is what we've been looking at so far, but if we can use this drop down here and we can switch to a trickle DAG, and you can see that the layout has completely changed. And this is it makes a really interesting structure if you add like a bigger file on it. But one thing to notice is that this CID up here, if we check it out, it's a QM. It kind of ends with CWESU. If I change to a balanced DAG, starts with QM, doesn't end with the same characters. And this is the same data. If we've not changed the data, all we've done is change the options here. And actually, if you change any of these options, then you'll get a different CID. So there's something to note there, or take heed of at least. You do get different CIDs if you change the different options, because the reason is that it may have more or less children, and those children will have different CIDs because they have more or less children. So it basically propagates all the way up to the top, and you just get a different CID for the same data. Now, if you've used the same chunking algorithm, then your leaves will probably still have the same data that can be deduped. But it will just be the intermediate nodes that have different CIDs. So there we go. There was a question?
Yeah, you said that there was the same data, but technically all of the blocks include links, which I think you mentioned, which causes the hash to change, and that's the main reason.
Yes,
because
exactly.
The link structure.
Yeah. So so I say it's the same data in that it's the same file data that was added to the DAG, but the intermediate nodes,
I see.
they are the things that are changed that are causing the root CID to have changed. Yeah, you're right.
So I think on that as well, then actually deduping, because you just changed the header, the hash of like whatever the truth is you're based on your DAG choice, will you get a lot less deduping? Like if the same file and two different DAG choices, it'll have not very much overlap in terms of what we're able to.
Yeah, if you change the chunker, then yeah, it won't necessarily be deduped nearly as well.
I guess I'm envisioning something like if I have a streaming service, the triple DAG makes a lot of sense. But if I have an archival service, maybe the standard default balance would be better. So it'd actually be two completely different files out there.
Yeah.
Very different.
Yeah. Yeah. So the thing is, this is all available as like options, but 99% of the time people will just be IPFS adding, and it should be doing the right thing. And I think we need to get better at actually building an appropriate DAG for the file you've added and for choosing a good chunker because of this.
But if I understood it correctly, the actual chunks will stay the same. So you still have a lot of deduping options.
Yes, yeah.
So
yeah.
you can imagine that.
But not if you change the chunk size
Right,
or the chunk.
but if you just change the DAG strategy.
Yeah.
So you can imagine a service that takes data that was added using a balanced DAG, restructuring it
Yep.
for streaming purposes.
Yes.
Mm-hmm.
That would be fairly cheap.
Yeah. Yeah. Exactly. Yeah. Yeah. That's interesting. All right. Cool. Let's move on a little bit. Okay. Immutable file system. Okay, so we've not got a lot of time left, so we're gonna. This is meant to be. Wait, when does this session go on till? 1:15?
I think so.
Okay. All right. Immutable file system. Okay, what is it? Well, let me explain. Okay, the MFS, the mutable file system, is an abstraction in IPFS that lets you deal with files in IPFS as if they were a mutable Unix-style file system. It takes care of the busy work involved when creating new DAG structures when you change files. So at a high level, you can kind of think of it like a tracking layer that maps paths to CIDs, and like a regular Unix-style file system, you work with paths, and you have familiar basic commands available to you, like move, copy, make dir, that sort of stuff. When you're addressing your cat gifs using the immutable hash like this, so not MFS, you have the whole IPFS network at your disposal. So if it's not found locally, then it will be delivered from another peer on the network, assuming it can be found. When you're using an IPFS path, like this path to my important business document, you're asking just your node for that file. If it can't be found on your node, then it will fail. So what I'm trying to illustrate here is that there's no global root MFS namespace. There's no kind of global Dropbox thing that we're all writing to. So yeah. But what you can do is you can turn that MFS path into a CID. You can use IPFS file stat, and it will give you more than the CID, but it gives you, so I can stat my business document.txt and I get back a CID QM.txt. And then we could share that CID with someone, and they'd be able to get that content from the peer-to-peer network. But you should be kind of careful when sharing a CID that you've got from your MFS system. Why? Well, okay, let's look into what happens when you edit files in MFS in order to answer that question. Okay, so adding content to a file. Let's say I store all of my notes on frogs in a file in MFS at /notes/frogs.txt. Okay, so what happens when I want to update my notes with a new? I've seen a new rare frog and I want to add it to the end of the file. Like you can imagine the path /notes/frogs.txt to be something like this in the DAG. So a UnixFS directory for slash right at the top, and that is the current MFS root. And IPFS keeps track of this. Everything that hangs off of that MFS root is safe from garbage collection. It won't be collected. So that's good at least. So what happens when we want to add some data to that file? We've got a new chunk, QM chunk 3, and that's got all of my notes on this new frog that I've seen in it. Well, we need a new node. We need an updated node which points at the previous chunks as well as this new chunk. So we've got a new node, a new CID for the frogs file that I have. And because we've got a new CID for the frogs file, we get a new CID and a new node for the notes directory, because, as I said, the CID for nodes is created from the data as well as the links. Because my link has changed, my directory has changed, and this propagates all the way up to the root. So qm/dir, we've got a new CID for the MFS root, and IPFS keeps track of that. So its new MFS root is this directory, and the nodes that I've grayed out here are now eligible for garbage collection. So they may be collected, depending on the settings of your IPFS node, they could be collected, whenever, in an hour, when you've added those more content, or never at all, you never know. But yeah. Okay, so back to sharing content. What have we learned? Well, what happens if you share a CID for a file with someone that you've got from filestat from your MFS thing, and then edit the file? Can anyone speculate? Right, it might be gone. So the CID for that file changes, right? The recipient doesn't get informed that that's been changed. There's no automated kind of, by the way, the CID has been changed. Like IPFS could never know that, because it wouldn't know that you've shared that CID with someone else. And it's also not, like the recipient is not guaranteed to be able to access that older content. Like they might be able to, because it might not have been garbage collected yet, but they might not be able to. Yeah, question?
Like, would it be useful to have some kind of update message?
Yeah, it would. But there's nothing kind of that does that automatic at the moment. Yeah.
Name stuff you can do that? IPFS?
Yeah, so you can.
Physically?
Yeah, cool. Okay. Yeah, going to talk about it. Yeah, I'm glad you're all listening. Cool. Okay, so this is the difference between kind of names and addresses, and MFS is names for content, but it says nothing about the addresses. So content addressing is has this restraint that content is immutable, yet we have this mutability layer on top of it. And so location addressing is kind of fun because we can change things and still get them at that URL, but we've already talked about the problems that are kind of apparent with that. We in IPFS have this thing called IPNS, which is a means of addressing mutable content. And so IPNS maps names to addresses, kind of like DNS maps names to IP addresses, but in a P2P system, it requires some kind of quorum over what the latest version of a thing is. So it can sometimes take some time to figure out what that latest version is before you get it. So there are some kind of issues with that. But yeah, IPNS is one way in which you can address mutable content. So you'd have to somehow stat the MFS root every time it changes and update your IPNS record to point to that new hash. So, I'm not going to go any more into IPNS in this session, but the rest of the time, which is now like 2 minutes, could someone pull the door too?
Oh, sorry.
Okay. Cool. We've got not very much time left, but I will point you at this brand new tutorial. We've got this site called proto.school, which teaches people about IPFS concepts. We've got a brand new tutorial for MFS that was built for Camp, and if you head on over to proto.school, that on the homepage you should see a link to the MFS tutorial, which will cover a bunch of the things that I've just talked about, but as well as there's coding exercises and all sorts that will kind of keep you occupied and help you learn a bit more about MFS.